In this lecture, we're going to go over turbines. A turbine is a device in which power is developed as a result of a gas or liquid passing through a set of blades attached to a shaft. They're used in power generation and in airplanes. If we properly select our boundary of our turbine, the kinetic energy of the matter flowing across the boundary is typically small enough to be neglected, so our energy rate balance reduces down to 0 is equal to Q minus work plus our mass flow rate times H1 minus H2. And often heat transfer can also be neglected, so we get that our work is equal to our mass flow rate times our change in enthalpy. To further illustrate this point of how heat transfer and kinetic energy can often be neglected, we're going to look at an example that says we have steam entering a turbine operating at steady state with a mass flow rate of 4,600 kilograms per hour. The turbine develops a power output of 1,000 kilowatts. At the inlet, the pressure is 60 bar and the temperature is 400 degrees Celsius. The velocity is 10 meters per second. At the exit, the pressure is 0.1 bar, the quality is 0.9, and the velocity is 30 meters per second. We're going to calculate the rate of heat transfer between the turbine and the surroundings. So if I write down our full energy equation, we have our heat minus our work plus our mass flow rate times our change in enthalpy plus our change in kinetic energy plus our change in potential energy. Well, we're still going to neglect potential energy because we're going to assume the inlet and outlet of the turbine are at the same relative height compared to everything else. So first we're going to look at the enthalpy difference. So we're going to look at H2 minus H1. So we have state 1 where P is 60 bar and T is 400 degrees Celsius, and at 60 bar T sat is equal to 275.6. Our temperature is greater than our saturation temperature, so we are superheated. So from table A4, we have H1 is equal to 3177.2 kilojoules per kilogram. At state 2, we're told the quality is equal to 0.9. We're given the quality, which is a dead giveaway that we are two-phase. So I want to go to table A3. H2 is equal to HF2 plus our quality times HFG2, which is equal to 191.83 plus 0.9 times 2392.8, which is equal to 2345.4 kilojoules per kilogram. So H2 minus H1 is equal to minus 831.8 kilojoules per kilogram. Next, we're going to look at the kinetic energy difference. So we have V2 squared minus V1 squared over 2, which is 30 squared minus 10 squared over 2 meters squared per second squared, which is equal to 0.4 kilojoules per kilogram. I encourage you to see for yourself that the units work out. So our heat transfer rate is equal to our work plus our mass flow rate times our change in enthalpy plus our change in kinetic energy, which is 1,000 kilowatts plus 4,600 kilograms per hour times minus 831.8 plus 0.4. So our heat transfer is equal to minus 62.3 kilowatts. So our change in specific, first of all, our change in kinetic energy is only 0.4 kilowatts compared to the 800 kilojoules that happens to be our change in specific enthalpy, which is why we can neglect kinetic energy changes for our turbine. Secondly, our Q is only 62 kilowatts, so it's small relative to the 1,000 kilowatts worth of power that we are developing. So again, we typically ignore both heat transfer and kinetic energy changes for a turbine. We're going to do another example where we have air expanding through a turbine operating at steady state. We know the inlet pressure is 150 psi and the temperature is 1400 degrees Rankine. At the exit, we know the pressure is 14.8 psi and the temperature is 700 degrees Rankine. The mass flow rate of the air is given as 11 pounds per second. And it tells us that 6,500 BTUs per hour of energy is rejected by heat transfer. We're told to neglect kinetic and potential energy changes. We have to determine the power developed by the turbine. We can neglect our kinetic and potential energy changes. So our work developed by the turbine is going to be equal to our heat transfer plus our change in enthalpy. State 1, P is equal to 150 psi and T is equal to 1400 degrees Rankine. Assuming the ideal gas law, we get H1 is equal to 342.9 BTUs per pound. We get H2 is equal to 167.56 BTUs per pound. I just looked up my temperatures in my ideal gas table of A22E. So my work is equal to minus 6,500 BTUs per hour. It is negative because it is work out of the system, plus 11 pounds per second times 342.90 minus 167.56 BTUs per pound times 3,600 seconds per hour. We get our work is equal to 6,878,464 BTUs per hour, or using the fact that 1 horsepower is 2545 BTUs per hour, we get 2,703 horsepower. In our next lecture, we're going to go over compressors and pumps.